And the presentation is open for discussion. So there is a first question in the chat line from Professor Svetlana Chilina, checking what is the charge of copper, which charge of copper corresponds to the total number of 167 electrons.
It's a 2+. So what I went on to do was to explore copper 3+. And this was what, yeah. What I'd gone ahead to do was to explore for the copper 3+, which is 168 electrons.
No. If your 167 is 2+,
yeah,
then removing one more 166 will be 3+, and adding one more 168 will be 1+, right?
Yes, sorry.
Okay. Did Lola answered her question?
Yes.
Okay.
What is the charge state of copper in the neutral complex? At 1+ or 2+?
2+.
So let me repeat the question. You answered in previous question that 167 is 2+. What is the charge of copper in 166?
Yes, in 166 it's 3+.
Is that 3+ stable? Do we know that copper 3+ stable in some complexes?
Can you return back to your file to your picture with energies? Yeah, this one. So where would be your 3+?
Right here. It's somewhere close to, right here. This is where the 3+ is.
So the difference in energy is within thermal fluctuation. So it seems possible to exist, to thermally populate.
And Lola, can you go to your DOS once, which you were showing with spin up, spin down?
Right here.
Yeah. So technically your DOS is not Omolola, right? So this is for, so your 66, this is neutral. So again, this is copper 3 and 67, 67 then would be copper 2 plus.
Right.
And this is the most stable structure. I mean, stable in terms of the energy.
It looks like copper 2 and copper 1 are approximately of the equal energy.
Yes. If I go back to the, it's somewhat close to each other.
But we're looking on a copper 2, right? For the so in this case, I think your Omolola, I'm a little bit confused with your spin down states, right? Because technically it looks like the lowest. What would be then? What would be your down state? What the gap if you really consider the different spin states? If you're not taking the gap between the same spin, but if you take the actual smallest energy independent on a spin, what would be then this gap?
Are you talking? Sorry, I didn't exactly get your question. Are you talking about in the beta position? I'm not sure what you're saying.
For the beta, you're showing alpha and beta, right? For what is on the top is your spin up, what is on the bottom is down, right? So my understanding that technically for your first case, 166 electrons, the actual gap is not coming from alpha and alpha states. It's coming from alpha, what you define red, field red, and then it should be taken unoccupied magenta line, which means you will have no gap in this complex at all. It's completely closing, right? Because technically, because in this complex, if spin orbit coupling is strong, then you can allow the transition with flipping the spin. And then you really have a transition from state, occupied state with spin up, to the unoccupied state with spin down, which has energy around -4, with both having the energy around -4. So your gap will be negligible. So you really don't have any gap in this complex.
Yeah, looks like it. Yeah.
And also, the same would be true for your copper 2, but for copper 2 in this case, you need to take. It looks like you need to take. In this case, I think it looks like they're pretty much the same energy up and down. Unoccupied levels are the same energy, or at least at this resolution, hard to say. But you need to take the gap between beta state occupied, right? Because your energy occupied beta state is now providing this highest occupied state corresponds to the spin down.
Right. LUMO alpha minus HOMO beta.
Or maybe also LUMO beta, because it's really hard to say.
No. In VASP, they always populate alpha with more spins than beta. It's just a convention.
Okay, yeah. So when you calculate your spectra, you calculating spectra independent on the spin, or you calculate the spectra only based on the spin up, spin like when you calculate the spectra, what exactly you which states are you taking into account in your calculation of the spectra?
Let me help. Answer is second option, spin is conserved.
Okay. But spin orbit couplings are included in these calculations or not?
Not here.
I see.
More questions to Lola?
Can I one
yes,
more?
Please. Yes, please.
I want to go back to the basis of the calculations. So you say that for a certain number of valence electron, you have like copper 2+. So some other number, you have copper 3+. How do you know it is copper 2+ or copper 3+? How do you know?
Are you talking about this slide? Sorry.
I mean, in general, like let's say that you do a calculation. Let's say for the total number of electrons equal to 167, and you said that you had a copper 3+, right?
Mm-hmm.
How do you know it's copper 3+?
That's a good question, because I wasn't exactly sure of which one.
Yeah, that's important, right? I mean, we may assume that it's copper 3+, but
yeah.
in reality, it may not be, what we expect. So you still have to check the output, the output of the calculation to confirm that.
It's not really true, because you're not expecting that oxygen will be positively charged, right? You're not expecting that DFT will result on a nitrogens being positively charged.
Well, would you please show the molecule itself a few slides before?
So you can easily, the only possible positive charge can be either on carbons and copper. But there is no question, if you're comparing copper and carbons, then for sure copper will be more positive comparing to the carbon, right? So there's really no such a big ambiguity in this case where exactly the positive charge will go, right? So you can estimate the total number of electrons based on the valence number of electrons for carbons, nitrogens, oxygens, right? Copper, taking copper 1, right? For example, you know how many electrons should be on a copper 1, so it's like 10 electrons. And so you know the total charge, you know the total number of valence electrons in a system, right? And then you can just, if you have neutral molecule, it means, because the ligands, these 2 oxygens on the bottom, right? So they actually losing the hydrogen, and they becoming negatively charged. So total the charge on the ligand is -3. And because to have this molecule neutral, the only way to have it neutral, the attachment group on the R is neutral as well. So the ligand is -3. So then to have it neutral, there is no any way rather than kappa being +3. If you make it to be -1, then kappa would be +2. If you make it -2, then kappa will be +1.
So that is true, and it may be clear in this case. but still, we still need some confirmation from the calculation, right?
Right.
But it's very easy to go into the archive file, look at the calculated local magnetic moment, or you can, plot the charge density. You tell the difference, and you see that, the extra electron or extra hole is going to be localized on copper.
It is much harder to calculate it in a VASP for this system, right? But it's much easier to get this information from the local basis set calculations with Gaussian. And I think Lola was checking these charges in Gaussian for seeing the difference in the charge on the copper between this kind of when she varies the charge on the entire molecule. Yeah, it's a good question. So when you talk about what is the charge, probably it's a good idea to confirm your results with some computational data.
Right.
Thank you for the discussion. More questions to Lola? Let me ask, just for curiosity, would you please show if do you have results for 168, like density of states and spectra for copper 1+, and do they show anything drastically different?
Yeah. So for like the density of states, looks like it's a singlet. Which I mean, singlets are more stable. So yeah.
Okay.
Yeah.
And it also has near infrared transition. Okay.
Yes.
So,
yes, it does.
More questions 1, more questions 2, more questions 3. Let's thank Lola once again.